Today we're going to talk about vectors. A vector is a quantity with both a direction and a magnitude. For example, if we say a westerly wind blowing at 15 miles per hour, the westerly would be the direction and the 15 miles per hour would be the magnitude. They are directed line segments, usually denoted by U, V, or W, have an initial and terminal point. When the ends are not specified, we use boldface lowercase letters. And of course, that's very difficult to do when you're writing it by hand. So if you're writing it by hand, normally we put an arrow above to denote that that is a vector. So if we look at this next one, it says vector is written as PQ with the arrow above, where P is the initial point and Q is the terminal point. So you would write it in order. So P, because it was before Q, would tell you that that's the initial point and Q is the terminal point. So P again is the initial and Q is the terminal. So this would be vector PQ with the arrow above. Standard position of a vector is the initial point at the origin, and the magnitude of the vector is the length of a vector denoted by, notice that we have the two lines, that means the magnitude of PQ, or if you were just using, if it was just vector V, you would just have the magnitude of vector V. And again, if we're writing it by hand, I would write it like this. Now, vectors are often confused with array that has a direction and an infinite length. It's really important to remember that a vector has a specific length, which is again the magnitude, and direction. So the arrow is just telling us the direction of the vector. It doesn't mean that it goes on for an infinite length. So I want to just make sure we're clear on that because, again, some students think that it goes on forever and it does not. So given vector V equals, and notice we have these two arrows that denotes that it's a vector with the component forms. So A comma B. So A is the horizontal component and B is the vertical component. We want to find the magnitude of vector V and the direction angle theta. So this is theta right here. So that's going to give us our direction. So component form of a vector has two components, the horizontal and vertical. And in this case, it told us since we had vector V is equal to A comma B, A is the horizontal component and B is the vertical component. So we know that this would be the length of A and this would be the length of B. And again, notice we're using the arrows on the end instead of parentheses to denote that this is a vector. So if I want to find the magnitude of V, that means I'm trying to find the length. So if we want to find the length, of course, we can use the Pythagorean Theorem. So we know that the magnitude of vector V, so since notice that's across from the hypotenuse, so the magnitude squared equals A squared plus B squared. So if I want to solve for the magnitude, I would just take the square root. So the magnitude of vector B is equal to the square root of A squared plus B squared. And if I want to find the angle theta, because I'm given the component forms A and B, I'm going to use those in order to help me find the angle. So this is a right triangle, so we can use our right triangle trig. So if we have opposite and the adjacent, we know we can use tangent. So the tangent of theta is equal to B over A, which gives us the direction. So we need to know both those formulas. So instead of writing a vector as an angle and a magnitude, we can write it as its x and y components. So just like we did in the last problem with A and B. So component here for x would be horizontal and y would be the vertical. So the component form with the initial point P being x1, y1 and terminal point Q, x2, y2 is going to be equal to the horizontal component comma the vertical component. So if you are given 2 points that are not in standard position, so not at the origin, then we would just subtract the, again, horizontal components comma the vertical components to write the component form. So when vectors have the same direction and magnitude, they are said to be equal. Note that you don't have to have the same initial and terminal points. So if we look at this first set, notice that they are the same magnitude, which is the same length, and the same direction, so these are equal. Looking at the next pair, we notice that the directions are different, so that's why these are not equal, because they have to have the same direction and the same magnitude. Looking at the next pair, we can see they have the same direction, but the magnitude is not the same, so the length is different. And the last pair that we have, we can see that both the direction and the magnitude are not the same, therefore they are not equal. So for this next example, it gives you P, the points P, which is 1, 2, Q is 5, 4, and then we have O, which is 0, 0, and R, which is 4, 2. We want to show that PQ equals OR. So we have to show that the direction and the length are the same. So let's go ahead and look at the magnitude first. So the magnitude of OR vector would be equal to, and in this case, because it's in standard position, we know that we can just draw a right triangle. And of course, this is the length of 4, and this is the length of 2. So we know that the magnitude would be equal to the square root of 4 squared plus 2 squared, because you're just doing the Pythagorean theorem. And of course, that would be equal to the square root of 20. And of course, we want to reduce that, so 2 root 5. So this is the magnitude for OR. So now we have to check the magnitude for PQ. So in checking magnitude, we can make our right triangle again. So now we have to subtract our coordinates since we're not at the origin in standard position. So the magnitude of PQ is equal to the square root of, and we're going to subtract the horizontal component, so 4 minus 2, and then plus the vertical component squared, so subtracting those, so 4 minus 2, sorry, was the vertical, and then the horizontal would be 5 minus 1 squared. And so when we do this, we'll notice that we get the same thing, because you can even count on your graph. So if we count 1, 2, 3, 4, you can see this is 4. So 5 minus 1 is 4. And for the vertical, we have 4 minus 2, which of course is just a distance of 2. So it ends up going to be the same as what we had for our first vector. So we know this is the square root of 20, which equals 2 root 5. So we just showed that both of these vectors have the same magnitude. And for the direction, we can look at the slope of our vectors. So the slope of PQ is equal to, of course, rise over run. So 2 over 4, which equals 1/2. And the slope of OR, again, rise over the run, so 2 over 4 equals 1/2. And remember, we can use the tangent because that's the angle. So the tangent opposite over the adjacent would give us, so the tangent of both of these give us 1/2 as well. So we can see that since PQ is equal to OR, because they have the same magnitude, and direction. So thus PQ equals OR because they have the same magnitude and direction. And we could write both of these in component form. So remember, the component form is always the horizontal component and the vertical component, which is the same for both of them since they're going with the same direction and magnitude. So PQ component form, of course, would be a horizontal component, which is 4, 2, which is the same as OR. So OR component form is also 4, 2, because they both have the same direction and magnitude. So that's the component form for both of them, which we'll look at in just a minute. So if we are given the initial point x1, y1, and the terminal point x2, y2, we want to find the magnitude of PQ. So, of course, to find the magnitude, since we're not in standard position, we have to find the horizontal component and the vertical component. So the horizontal component, since this is x2 and this is x1, you would have to subtract x2 minus x1. So this would be x2 minus x1, and the vertical component, you subtract the y, so y2 minus y1. So the magnitude of PQ vector would be equal to the square root of, because again, you're just doing the Pythagorean theorem, so the horizontal component x2 minus x1 squared plus the vertical component squared, so y2 minus y1 squared. And we just looked at that in the last problem when we found the magnitude of PQ up here using those 2 points. That's why we had to subtract. So again, that's for when you are not in standard position. All right, so for the next example, it says find the component form and magnitude of a vector v with the initial point at 4, -4, and terminal point at -1, 5. So we have 4, -4, and -1, 5. So let's go ahead and get our straight line tool. So this is the initial point and the terminal point. All right, so that is our vector v. And we want to find the component form. So remember, the component form means that you are looking for the horizontal component and the vertical component. So the component form for this would be equal to, and we have to, of course, subtract the points to find the horizontal and vertical component. So we're going to subtract the x's and then subtract the y's from always the terminal point minus the initial point. So the terminal point is x value of -1 minus the initial x value, which is 4, comma, and then the terminal point y would be 5 minus the initial y, which would be -4. So when you are subtracting, remember, order does matter. So terminal point minus the initial point. So then that means our component form for vector v would be equal to -5, 9. So even on the graph, we could see this if we were to go the horizontal component. So this would be -1, 2, 3, 4, 5, because we're going left 5, and up the vertical. So this vertical component, notice if you were to count, is 9. So the component form again would be -5, 9. And if we wanted to find the magnitude of this vector, so the magnitude, remember, is looking at the length. So we have the horizontal and vertical component. We just need to square those because, again, this is a right triangle. So that means that -5 squared plus 9 squared would give us the square root of 106. which does not reduce, so this is the magnitude of the vector. And of course, we could also find the direction by doing the tangent. So the tangent of this would be negative 9/5. So let's go ahead to the next problem. And I just wanted to mention again that the component form is when you're not at the origin, is the terminal point minus the initial point. All right. So let's go down here. It says, example, find a vector equivalent to vector PQ with its initial point at the origin. So if we want the initial point at the origin, we're basically looking for our component form. So again, we're going to do the terminal point minus the initial point. So over here, it told us that the initial point is P and Q is the terminal point because, again, the order that it's in is PQ. So the first letter is always where you're starting. So for this PQ, the component form would be equal to, and in this case, we have our terminal point. So the x coordinate is -2 minus the initial x coordinate, which is 2, comma. The terminal point vertical is y, which is 9, minus the initial point vertical component, which is, or vertical coordinate, which is 7. So that's going to give us, if we subtract, equal to -4, comma 2. So this is the vector that is equivalent to PQ, but its initial point is at the origin. So we know that they're the same. We're just moving our vector to the origin by putting it in the component form. So it gives us the horizontal component and the vertical component. So if we do B, same thing. So for this one, we have -7 minus -5, comma, -9 minus 6. So this would be equal to -2, comma, -15. So that would be the component form, placing it at the origin. So vector operations, scalar multiplication and vector addition. So when you are adding vectors together, you just add the horizontal components plus the vertical components. When you're multiplying, doing a scalar multiplication, you take that scalar and multiply both the horizontal component and the vertical component. So it just makes the vector, of course, longer or shorter. And if your scalar k is positive, then it has the same direction as your vector, but if it is negative, it's going to go in the opposite direction. So that is something that we want to make sure we point out. So if we look at this first vector v, if we did half of v, so notice then the length is half of what it originally was. 2 times v, notice that it is twice as long as this original vector v that we have right here. This is the original vector. Notice that -v goes the opposite direction. And then the last one we have is -3/2 v, which is again opposite direction. So that would give us our vector operations. All right, vector addition is when two forces pull in the same direction upon a single object. So vector addition, if we have a vector u plus v, we would add the horizontal components and then the vertical components together. So graphically, the initial point of one vector coincides with the terminal point of another vector. The sum is head to tail. Sometimes it's called the parallelogram law, which we'll look at in a second. So when you add those vectors together, it is called the resultant, which is important when we're doing applications. So over here, if I were to add these two vectors together, the resultant would be this this vector right here. So notice that, again, it's always heads to tail when you are adding the vectors together, and the resultant would be from this, where we started, all the way to the terminal point of the second vector that you're adding. So this is vector u plus vector v. And of course, you don't have to add them in this order. So this would be u plus v, but let's say we did v plus u. That's why they call this the parallelogram law, because we could have, if you look at the component form of v, let's see, our horizontal component is over 1, and our vertical component is up 1, 2, 3, 4. So it says, given the graph to right, find the component form for u and v. So v component form is 1, 4. And our component form for u would be over, starting at the initial point, so right 1, 2, 3, and up 1. So 3, 1. So those are our component forms. So I'm going to go ahead and over here, if I were to instead go over 1, up 1, 2, 3, 4, that would give me my vector v, and then vector u is over 3, 1, 2, 3, up 1. So notice that this is vector u. So if we were to add vector v plus vector u, notice that it gives us the same resultant. So that means that they are equal. So I could do vector v plus u or vector u plus v. So the next question is asking, what is the resultant of u and v? So that means the resultant, we are going to add the components together. So I'm just going to rewrite them over here. So we have u, which is 3, 1, and v, which is 1, 4. So if we were to add these together, u plus v would be equal to, so 3 plus 1, of course, is 4, and 4 plus 1 gives us 5. So this is our resultant. So 4, 5 is the component form. And you can even see that if you looked at your graph here. So from the start, this point, we have to go right 1, 2, 3, 4, and up 1, 2, 3, 4, 5 to get to the from start to the finish for the resultant vector. So that's another way you could graphically actually see that the component form would be 4, 5 for the resultant. So the next example, say let vector v equal -2, 5 and w equal 3, 4. We want to find 2 times vector v, so that's a scalar. So that means we're just going to be multiplying 2 times -2, 5. So remember, for scalar multiplication, you just multiply. It's like distributing. So 2 times -2 would give us -4, and 2 times 5 gives us 20. So this would be our 2v. Then vector w minus v. So when you are subtracting, order, of course, does matter. So in this case, we have 3, 4 minus -2, 5. So in this case, we have w minus v means we have to do 3 minus -2, 4 minus 5. So that gives us 5, -1. So that would be my answer for vector w minus v. And vector v, which is -2, 5, plus 2 times vector w, which is 3, 4. So this would be -2, 5, plus 6, 8. So we have -2 plus 6, comma 5 plus 8, which is equal to 4, comma 13. So that would be our solution. All right, so next we're going to look at direction angles. So the angle theta that represents the direction of a vector in the plane is the standard angle from the positive x-axis to the vector when it's in standard position, kind of like when we did, talk about the unit circle, it's the same idea. So given vector v is with component form a comma b, so we want to find the direction angle theta. So theta would start here, go this way. So that would be the direction. And then this, of course, is A and B. So we talked about this already, that the direction to find this, we can use right triangle trig and tangent since we're given the horizontal and vertical component. So the tangent of theta would, of course, be equal to B over A is what we use. So that means, of course, to solve for the actual angle, we have to use inverses, because the only way to get the angle out is to do the tangent inverse of B over A. And recall, when you're doing the tangent inverse on your calculator, or taking the tangent inverse, remember that it only gives solutions in quadrants 1 and quadrant 4, because we talked about that when we did our inverses for sine, cosine, etc. So the original problem doesn't have an inverse in it, but when we do this in our calculator, because that's what you're going to use in order to find the actual angle, if it's not on your, of course, unit circle, then we have to think about, well, if it's not in quadrant 1 or 4, we're going to have to do something a little bit different to find the angle, which we'll take a look in these next examples. So for this, it says find the direction given each vector in component form. So if I want to find the direction, we first would draw a picture. That helps me. So notice that the horizontal and vertical component for this first one are both positive. That means we're in quadrant 1. So we're going over 5 and up 3. So that means that the tangent of the angle would be equal to opposite over adjacent, so 3/5. So if I want to find the direction angle, we would do the tangent inverse of 3/5 on our calculator. So if I get my calculator out, we want to make sure, of course, that our mode is in degrees for these. So we're not going to be using radians for vectors. We're always using the degrees. So make sure you're in degree mode. And then tangent inverse of 3 divided by 5 gives us 30.96. Going to round to the nearest hundredth here. So 30 theta equals 30.96 degrees. So that is the direction. Looking at the next one, we have vector v is equal to 5, -3. So this one was quadrant 1. Now notice that we're in quadrant 4. So that would be my vectors. We're going over 5 and down 3. So for this one, the tangent of theta is now equal to -3/5. So theta equals the tangent inverse of -3/5. And if we plug that into our calculator, so the tangent inverse of now -3 divided by 5, notice that we get -30.96 degrees. Of course, if you wanted to find the coterminal angle to that, you could add 360 degrees. So if I added 360, the coterminal angle that's positive would be 329.03 degrees. We could also use that as our direction. So you can use that coterminal angle and just be the positive angle measurement. So the next one, notice that is negative 5, 3, which is quadrant 2. So if I draw my vector in quadrant 2, so we have negative 5 and up positive 3. So the tangent of theta equals 3 over negative 5. So theta equals the tangent inverse of negative 3/5. Well, we just did that, right? So we said the tangent inverse of negative 3/5 was equal to negative 30.96 degrees. Well, we know that cannot be our answer because remember when you do the tangent inverse, you're getting answers in quadrants 1 or 4. So this is the answer in quadrant 4, which is right here. So if we want to find the answer in quadrant 2, notice that is 180-degree difference. So the difference from here to here is 180 degrees. So if you have answers in quadrant 2 or in quadrant 3, whatever you get for your angle, you're going to have to add 180 degrees to. So if I add 180 degrees to this, that's going to put me in quadrant 2 because we know our answer can't be in quadrant 4. So theta would be equal to 149.04 degrees. So that's what makes these a little bit harder, is that if you get a vector that's not in quadrant 1 or 4 and you're trying to find the direction, you have to add 180 degrees to your answer. Same thing if we're in quadrant 3 like this next one. So for this next one, we have our vector, so negative 5 and negative 3. So the tangent of theta equals negative 3 over negative 5, which is of course 3/5. So theta equals the tangent inverse of 3/5, which we did on the first problem A. So we know that that's equal to 30.96 degrees. But we know that that is quadrant 1. So this is 30.96 degrees. We need to figure out what the angle is for this, the direction for this vector. So we need to figure out this, of course, distance here. And in order to do that, that means, again, notice that from this vector to the other side is 180-degree difference. So we're going to add 180 degrees to the 30.96. So that means theta is equal to 210.96 degrees. So again, be very careful about the direction when you are finding these if you're in quadrants 2 or 3, because like we said when we did our unit on trigonometric inverses, we had those specific rules. So we know that we want the angle to be in the correct quadrant. So that's why we're, again, adding that 180 degrees. So that is all for vector basics. And of course, we're going to do vector applications in the next video that we have.